So everyone, on behalf of the Earth, Atmospheric, and Planetary Physics Group and the Department of Physics, it gives me great pleasure to welcome you to our 2022 Nobel Lecture Series. These lectures began in 2003 and have been made possible through the Reginald and Muriel Nobel Fund. So before Professor Griswold introduces our speaker for the week, I'd like to say a few words about our benefactor, Reginald Nobel. He was born on a farm in Clinton, Ontario in 1911. He did a bachelor's in honors math and physics at U of T in 1934, followed by a master's degree in physics, specializing in meteorology, also here at U of T. He then moved on to the Meteorological Service of Canada, where he had an illustrious career, eventually becoming Assistant Deputy Minister. He was posted to Newfoundland in 1937 and was officer in charge of the new District Aviation Service in Montreal and established a weather forecast office in Halifax all before age 30. Between 1940 and 1946, he was in charge of a program seconding almost 400 newly trained meteorologists to Royal Canadian Air Force bases and was meteorological advisor to the Royal Canadian Air Force Chief of Staff. After the war, he moved to Toronto, playing an important role in an era of rapid expansion of what we now call Environment and Climate Change Canada, including the move to the building at Downsview that many of us know well. Mr. Nobel was known as a highly skilled administrator, quiet and full of common sense. He was also keenly interested in science and the happenings at the University of Toronto. We believed he must have enjoyed his time in the physics department significantly, as he left a very generous endowment to the Atmospheric Physics Group, which has allowed us to establish this lecture series in his honor. We are all grateful to Reginald Nobel for his generosity. And with that, I would like to invite Professor Griswold to introduce our speaker for the week.
Hello, and thank you for coming, and thank you for watching online. So it's a great pleasure for me to be introducing Professor Raffaele Ferrari, Raf. So he hails from Torino when he earned his bachelor's and master's degrees and one PhD degree in fluid mechanics in '99. He also got another PhD degree in oceanography at Scripps in San Diego, as Italians do often. So I'm supposed to not say too much because he will have, many of our students will introduce him 4 more times. So I will just say that me as a physical oceanographer, so Raf in the 2000s worked on a series of review papers that have guided our entire community. One of his big achievements in a career that is actually not that long already has been to really work on what do we need to understand about the ocean to understand its role about the climate. And these review papers have been really guiding pieces of work for us to constantly refer to and know where to go and see how we're relevant. So, and I believe this talk is in that tradition. So without further ado, I will let Raf talk about abyssal mixing.
Okay, thank you very much for the introduction, and apologies for not being there in person. I was supposed to fly this morning, but my flight was canceled, so I hope to be there in person tomorrow. But at this point, I don't promise anything because I don't know what to expect from the airline industry. And it's a pleasure to get to present some of the works of the various work that my group has been doing over the last few years in various areas that relate to the role of the ocean in climate in various aspects, ocean and atmosphere. At least some of the lecture will touch on the atmosphere. But today, what I'm going to try to articulate is a bit the role of abyssal mixing. I write here in climate, and indeed we'll discuss about the implication of abyssal mixing in climate. But what I hope I try to inspire people to think that there are still fundamental questions in oceanography that are not fully understood, and observations that are highlighting new aspects of the ocean circulation that we weren't aware of. So here I'm trying mostly to emphasize the new aspects that are still being discovered in the dynamics of the abyssal ocean. I put here a nice picture from the abyss, if it's the abyss, I guess. It's a movie made by Hollywood, and what I write is the title there that says, "This is a place on Earth more awesome than anything in space." And I guess it's the only case where I'm working on something in oceanography that Hollywood will rank above planetary or extraplanetary research. So let's get started, and we'll have to bit understand what is the role of the ocean in climate, and then focus on the abyss in particular. And please feel free to interrupt me at any point. If people put anything in the chat, it would be great if somebody monitors the chat so that I know, and they let me know if there are questions coming in. So let's start with the role of the ocean in climate. Well, the ocean is a big heat reservoir of the climate system. Just for context here, I'm just showing a section as a function of depth and latitude from the Pacific of temperature in the ocean. But just to make the point that if we look at the amount of heat contained per degree Kelvin in the ocean, we have something like 5 × 10⁻²4 joules. That's called yotta-joules. But the main point is that per degree Kelvin, the ocean stores 3 times as much heat than the atmosphere. That's because it has a larger heat capacity. That's going to be very important because it's this very large reservoir of heat, and most of that heat is contained just by volume in the abyss, like below 1,000 meters or so. And so indeed, the abyss is a large heat reservoir. The second large component that we touch on partly in this lecture, but more in the following lecture, is that the ocean is also a large reservoir of carbon in the climate system. The ocean contains of the order of 40,000 gigatons of carbon compared to, well, 760 at this point. We're close to 800 gigatons of carbon in the atmosphere. So most of the carbon in the atmosphere, ocean, and land system is actually in the ocean. So again, the ocean plays a big role in the carbon cycle. And again, from this section, again, from the Pacific as a function of depth and latitude, you see that a large fraction of the carbon, of the largest value of carbon, are actually in the deep ocean. So again, the abyss plays a big role in storing additional carbon. Indeed, our carbon dioxide concentration in the atmosphere would be much larger if the ocean was less efficient in storing carbon. And this is in particular in the last lecture series of this lecture, we'll touch about why there is this subsurface maximum in carbon concentrations. But just to show that these are not just vague statements about the role of the ocean in climate, but they really do matter, is I can show as a function of time. Let's start with the, oops, that, oh, what happened? Sorry. What did happen? Okay, I'm back, sorry. We start with the left panel. This is a panel from the 2015 IPCC, is the Intergovernmental Panel on Climate Change report. And they are showing for us, starting from 1970, from the beginning of the instrumental record on a global scale, the increase in heat content in the Earth system. And it's divided in its various components, meaning in the ocean component, that's the blue part. The pale blue is the upper ocean, the dark blue is the deep ocean. And then there are small slithers that show the amount of heat that is taken up by melting ice, and then an comparable slither that is changing land usage. So heat uptake on land, and then the atmosphere is this purple, very thin slither, just to show that 93% of the excess heat that the Earth system is trapping because of increasing greenhouse gases concentration ends up in the ocean. It's because it is this very large heat reservoir. This is not to say that the ocean is warming faster than the atmosphere, because for the same reason as mentioned before, the atmosphere has a much smaller heat capacity. So even though it stores very little heat in terms of temperature, it's increasing in temperature faster. But what it's telling us is the ocean is a fundamental aspect of this heat budget. And it's thanks to the fact that the ocean is absorbing a lot of heat that we are delaying the warming that we would otherwise see if the atmosphere was taking it all up by itself. Oops. And on the right side of the panel, instead, we are looking at the increase in carbon. This picture is a bit different. It starts from 1750 and goes all the way to the present day. In the upper half of the panel, we are looking as a function of time, the increase in emission of carbon dioxide and changing carbon concentration or emission in the atmosphere because of changes in land usage. This is the brown one. But what we care about is the lower part of the panel that shows us where this excess carbon that is emitted in the atmosphere, in the Earth system ends up. And we see that the green one is what ends up in land, the pale blue one is what ends up in the atmosphere, and the blue one is what ends up in the ocean. So half of the carbon remains in the atmosphere, what excess emission we are emitting into the atmosphere, and then a quarter and a quarter or something like that ends up in land and in the ocean. So again, the ocean is a large and important reservoir of carbon. It modulates our carbon emission. Of course, if we stop emission suddenly, then a lot of the carbon eventually ends up all into the ocean as the system re-equilibrates. Start from the Charney report is one of the first reports addressing the issue of climate change and the potential for climate change because of anthropogenic emission, was already pointing out that it is quite possible that the capacity of the deeper oceans to absorb heat has been seriously underestimated. So more to point out that indeed the role of the abyssal ocean in this budget is both poorly understood and potentially of serious impact in projection of climate change. So how does the heat enter in the deep ocean? And this is just a schematic, just to introduce us a bit to the question. And what I'm showing here is a schematic around Antarctica. So this is the Antarctic continent with its sea ice, and where it's red, it shows there is warming, that we are already observing warming with mostly float data. In this schematic is a review by Saleh et al. On the available Argo float profiling program that is sampling continuously the ocean. And we see that most of the heat is for the moment entering in the upper ocean. This should be the upper 1,000 meters or so of the ocean, but there is already some plume of warm water that is entering all the way into the abyss. This is measured instead more directly with vertical profilers all the way down to the ocean bottom. So we see that heat can enter and intrude in the ocean by entering directly down into the abyss. And over time, the amount of heat that will enter into the abyss will increase proportionally to what is at the surface. So we expect that the ocean will play more and more of a role as we move towards the future in this heat budget. And the question is that we want to understand what sets the rate at which this heat is entering into the deep ocean. So let's now move in practice to discuss what is the abyssal ocean, what I mean by the abyssal ocean. And just as an operational definition, I'll start by showing a picture of density in the ocean. So this is depth and latitude. We go in the Pacific Ocean between Antarctica and all the way to the Bering Strait. And these contours show density. And so you see that the ocean go from light to dense. It can be thought as a set of layers of density that is progressively increasing towards the ocean bottom. Let's for the moment not consider this part on the south, which is what we call the Southern Ocean, which is a bit special. But let's focus for a moment instead in the Pacific itself. And what you see, density surfaces here are pretty flat, while they are strongly deformed from a flat profile in what we call the upper ocean. Here it's because the wind have a direct effect on the winds, on the stratification. They push warm water into the interior. So this is what we call the upper ocean, where wind influence is very strong. Then we have what we call this intermediate layer of deep ocean, where density surfaces are pretty flat. And then if we go deeper enough, isobicas, then again, they start becoming a bit deformed. More importantly, this deeper ocean, so anything below, somewhere between 2,000 and 3,000 meters, is strongly affected by the presence of bottom topography. The typical height of ridges and seamounts in the ocean rises up to 2,000 meters, or a bit less than 2,000 meters, because of isostatic adjustment and other ideas, but that doesn't matter. So what matters is that the abyssal circulation is that circulation in the deep ocean that is strongly affected by the presence of topography. This part of the ocean is strongly stratified, meaning that density still increases towards the bottom. So that's one thing we have to remember, is whatever theory and understanding we build on, it has to account for the strong stratification in the deep ocean. The deep ocean is also characterized by a strong circulation. And this is what I'm drawing here. Now, this is again, depth and latitude. In this case, it's a zonal average using observation from all ocean basins, meaning the Atlantic, the Pacific, and the Indian Ocean. And we are averaging together, and we're looking at these contours now are streamlines. So it's the flow followed by water as it moves across the ocean in depth latitude space. We see that there is water sinking around Antarctica that sinks to the ocean bottom. This water then returns upward, but upward always below, and you see this gray line that I hope you can detect here. That is the typical height again of topographic features like sea ridges and seamount at around 2,000 meters. the circulation rises, and clearly mass cross density surface to rise, and this water comes back, but it never reaches above this topographic feature, just sits below it. So it's a circulation, and this is what we really call the abyssal circulation, that is strongly affected by the presence of topography. There is a second cell that rotates in the opposite direction. This is mostly sitting in the Atlantic. This is a zonal average picture, so we cannot tell what is what. Water is sinking at high latitudes in the Atlantic, then it's moving all the way to the Southern Ocean, hardly changing any density. And the circulation mostly sits above topographic features, and which already is suggesting that in order to cross density surfaces, probably topography has to play a role. Here there isn't much topography, and therefore density surfaces are not crossed. Until the water comes into the Southern Ocean, all waters come to the surface in the Southern Ocean because there are winds that create very strong divergences and suck water towards the surface. So what we want to understand is a bit what is the shape of the circulation. The circulation mostly lives in the Pacific, but it also has, and in the Indian, but it also has a slight projection in the Atlantic. Well, the upper one that we're not going to discuss today lives primarily in the Atlantic. And as I said, from the abyssal perspective, it's not as mysterious because water just flow at a constant density without changing their property. So the first question I want to briefly address is that, well, where does the water sink in the abyss? Why is it happening at this high latitude? So that we are all on the same page. And we see this is the part of the problem that we do feel we have a good handle on. If we are looking at buoyancy fluxes at the surface of the ocean, and this is the map you see here now, this is latitude and longitude, so the surface of the ocean, you see Africa, Asia, the Americas. Where there is red, it means that the ocean is losing a lot of heat. We see that where the ocean loses most heat is in this region that are associated with what are called in the oceanographic literature western boundary current. These are very fast currents that bring warm water northward, and therefore you have a very warm anomaly next to a continent. When the area from the continent that is cold arrives here, you get a lot of heat loss. So the largest heat losses are here, but these are also regions where stratification, the vertical change of density with depth is very fast. And so even though you cool a lot at the surface, particle cannot be mixed very deep because the ocean gets denser quite rapidly with depth. So the particle never get dense enough to sink very deep. Instead, it's at high latitudes where the stratification of the ocean is much weaker for reasons that at least the physical oceanographer will know. Here it's because the winds actually pull water toward the surface and reduce stratification by doing that. And so you have weak stratification and significant but not anomalously large heat fluxes. And then all of a sudden, just a bit of cooling, if there isn't much stratification, we make the water at the surface dense enough that it can sink all the way to the ocean bottom to reach its neutrally buoyant level. So we understand why convection essentially is confined to really 4 seas in the ocean, the Labrador and the Greenland Sea in the North Atlantic, and the Ross Sea and the Weddell Sea around Antarctica. We can actually see firsthand the circulation sinking in the abyss. You see, for example, this is a section of the Atlantic, and it's a salinity section in this case of the Atlantic, again, depth. This is around Antarctica all the way to the Greenland and Labrador seas. And what you see is there is this tongue of very high salinity that sinks into the ocean abyss. These are water that, for reason that I'm not discussing here, but they have high salinity. And so salinity here is just used as a tracer to track the water mass, but you really see this water sinking and essentially flowing in the ocean interior at a depth of around 2,000 meters. So this water is formed through convection and just flows towards the Southern Ocean, carrying its signature of salinity. You can also see a plume of somewhat fresher, but well, a plume of water of intermediate salinity that is sinking from around Antarctica and sinking in the deep ocean. It's less salty than this water here, and it's less salty than the North Atlantic deep water, as it is called, but definitely saltier than the freshwater tongue above it. But again, as a tracer, we see that this water is sinking and carrying a plume of water that is the signature of this convection around Antarctica that forms the denser water in the ocean that really sinks all the way to the ocean bottom. And this is the part of the circulation we want to focus on, because you see that this circulation is going to interact with topography, not the one above. We see the same signature in the Pacific Ocean. Here now it's again salinity and it's a function of depth, but now this is around Antarctica all the way to Bering Strait. And now you see this high salinity signature, this water sinking around Antarctica and flooding into the very deep Pacific. So this is the circulation. So we see why we know the water is forming just a few places. We do see these sources of water sinking into the interior. What we don't see is that we know that in equilibrium, this water has somehow to return to the surface, but there aren't obvious signatures of water carrying salinity plumes towards the surface, carrying its signature. So the question from early on in oceanography has been, well, how does the water come back to the surface to achieve an equilibrium? Because that's what must be close in this overturning circulation in the abyss. The story starts very early on. I guess in terms of early theories, the first clear report of what we might call hints of an overturning circulation comes from Henry Ellis, a captain of the British slave trader Earl of Halifax. I find it's important just to remember that, even our science is very entrenched with history. So Henry Ellis might have made some interesting scientific observation, but he was also a slave trader. So there is a mixture of good and bad that we have to deal with in looking at our history. But from the point of view of what Henry Ellis was contributing, he just pointed out here he was navigating along very warm waters in the tropics and said the cold increased regularly in proportion to the depth till it descended to 3,900 feet, from whence the mercury in the thermometer came up to at 53 degrees Fahrenheit or 11 degrees Celsius. This experiment, which seemed at first but mere food for curiosity, became in the interim very useful to us. By its means, we supplied our cold bath and cooled our wines or water at pleasure, which is vastly agreeable to us in this burning climate. Now, the fact that what he was pointing out is that pretty close below the surface in the tropics, the water was as cold as you might have expected it to be at high latitudes close to the poles. The fact that he could use it to cool water, well, might have been useful, but it's beyond the point. What was important, he decided to send these results to the academies in England, and Benjamin Thompson, by looking at these results, said, okay, so this could be interpreted. Seems to be suggesting something quite important about the deep circulation of the ocean. We know that there must be cooling at high latitudes and heating at low latitudes. That's why the water is warmer at low latitudes than at high latitudes. So probably the water sinks through what is a convective event. This is convection is a problem that Benjamin Thompson was studying, meaning how do you drive motions with change with heating and cooling. And so he assumed that the water was cooled, becoming dense and sank to the abyss, and then it was returning toward the surface in the tropics. And that's why you got this cold water close to the surface in the tropics. So that was his explanation. Now, the problem with this explanation, as we know, and it was realized pretty soon after Benjamin Thompson made his statement, and through this schematic, actually this is a schematic by Lenz, but based on ideas of Benjamin Thompson, was that the ocean is not transparent to electromagnetic radiation. What it means is that all the heating and cooling that arises from the atmosphere penetrates no more than 100 meters from the surface. So water here is not directly heated by radiation. So the question was, well, how can a water parcel that is very cold here all of a sudden become warmer if nothing warms it up? And so for a while, the idea was abandoned. It seems that there was a problem with this picture because clearly you couldn't have water rising up. So that you understand the atmosphere is very different. This picture actually applies to the atmospheric circulation to some extent because the atmosphere is transparent to electromagnetic radiation. So the heating at low latitudes reached all the way to the Earth. So you're warming the bottom of the surface below the atmosphere, and that drives rising motions. And high latitude, instead, you radiate radiation out and you can cool. So indeed, you can have heating and cooling within the atmosphere, but in the ocean, heating and cooling directly from electromagnetic radiation enters only at the surface, cannot drive such a simple circulation. So this is something that I found out as I was preparing these lectures. So the first attempt at coming out with a real formal theory of the abyssal ocean circulation comes out 2 centuries later with work started by Henry Stommel at the Woods Hole Oceanographic Institution. And apparently the first time it was presented to the oceanographic community was in 1957 on September 5th through 6th here, here or there in Toronto. So there was a general assembly of the International Union of Geodesy and Geophysics in Toronto, and Stommel comes up with what I described as the beginning of a modern theory of the ocean overturning, deep circulation. So Stommel started arguing from this point of view, as we said, is that we have this cold water sinking at high latitudes. This is the source. We've seen that there is evidence that water sinks at high latitude in large amounts. Actually, we now know from direct observation, I didn't point it out before, but the amount of water that goes into that blue loops that I call the abyssal circulation is of the order of 15 Sverdrups. That's 15 times 10 to the 6 meter cube per second. So that's how much water sinks into the abyss. And Stommel argued that since we don't see any obvious evidence of water coming out in plumes somewhere in the way maybe Benjamin Thompson would have predicted, he just assumed that the water must be probably upwelling very slowly everywhere in the ocean and coming back to the surface uniformly. So he said, well, if I want to know what is this upwelling W, the vertical velocity that balanced this sinking, well, I can estimate it as the ratio of the amount of water that sinks at high latitudes, this 15 Sverdrup or 15 times 10 to the 6 meter cube per second, for example, divided by the area of the Pacific, because it's the Indo-Pacific, because that, as I said, this is where most of that circulation lives in. That is 1.6 10 to the 14 meters squared. I divide the two numbers, I get an upwelling of 3 meters per year. That's a very slow velocity, as you can imagine. And so it's something that you wouldn't necessarily measure, and you wouldn't even see in tracer because it's so slow that tracer probably gets mixed and diffused away before the water comes to the surface. So that seems to make some sense. It's just the water or that circulation is so slow in its vertical component that we wouldn't see it. Stommel then went to make some prediction of the horizontal structure of the circulation, but not necessarily what we care about, this overturning loop in the depth latitude space. The person who made progress on trying to understand how you support that circulation is instead Walter Munk in a very celebrated paper at this point, Abyssal Recipes. By the way, if you're not a physical oceanographer, the two most distinguished figures in the field of modern oceanography are really Henry Stommel and Walter Munk. So these are the two names you want to remember. So Walter Munk comes to the picture and says, well, let me look back at the stratification of the global ocean. So this is depth and latitude. And again, we see that these density surfaces are pretty flat in most of the abyssal ocean. And so he said, well, so the buoyancy is just density anomaly. If you want, is rho minus rho naught divided by rho naught. The ocean has a density that changes just by a few percent. So it's easy to just talk about relative changes in density and multiply by g. So it's like an acceleration. So it's an acceleration that you feel in the water parcel if you are slightly different from densities around you. But in any case, you can think about this as a buoyancy budget, as a temperature budget, or as a density budget. It's the same thing. And what Munk argued is that probably these horizontal advection terms are pretty small because horizontal advection, horizontal gradients in buoyancy are pretty small in most of the deep ocean. So maybe it's the vertical advection that is balanced by, and he said there must be some diffusion, right? Some heat must be diffused downward in order to allow this water to rise in the vertical across the density surface. There must be some diffusion of heat in the interior. And what he proposed to do was indeed to use this balance between advection, meaning the vertical advection bringing cold water up, balanced by diffusion of heat downward, and he used the Fickian law with some diffusivity that he didn't know quite yet what it might be at this stage. And so he said, this is the balance that I believe should hold in that stratification. And this equation, if I assume that both W naught and kappa T are constant, it just has exponential solution, and when the heat folding scale is given by kappa T over W naught. So now Munk was very creative in connecting theory to observation. He said, now I can take a profile of temperature in the ocean. He just went off in the middle of the Pacific and look at the vertical profile of temperature. The dots are measurements that he took. He just looked at a very few profiles in practice of potential temperature. Then he did it also with density, meaning with buoyancy. And he just said, well, I can fit an exponential function to this profile. And I find that the exponential function that fits best the data has an e-folding scale of around 800 meters. That means that kappa T over W naught is of order of 800 meters. And since I have some intuition for what W naught might be from the work of Henry Stommel, then I said the kappa T should be equal to W naught times 830 meters, or 10 to the minus 4 meters squared per second. So he said, if this budget is going to hold, I need a diffusivity, which represents the rate at which heat is diffused in the interior, as large as this number. To be fair to Stommel, he actually went a bit beyond this. He also looked at the same budget for a different tracer, carbon-14, which has a decay rate. And so that becomes a second independent constraint. So once you have two independent constraints, you could actually estimate independently kappa T and W naught and not rely directly on the estimate of Henry Stommel. So he also did the full exercise, but he got pretty much again the same number. So the surprise here, at least at the time, was this kappa T is order 10 to the minus 4 meters squared per second, which is much larger, 3 orders of magnitude larger than molecular diffusion. So he said, I'm heating with electromagnetic radiation at the top of the ocean, and that heat wouldn't really penetrate very much into the interior to maintain the stratification we observed. There must be something more efficient that mixes heat into the ocean interior. And as you've all experienced when you put sugar in your coffee, you just don't wait for molecular diffusion to mix the two. It will take a very long time and you would never drink a warm coffee. I'm Italian talking about coffee. You can apply it to tea if you prefer. In the ocean, what Walter Munk was suggesting is that there has to be equivalent of some spoon that are very effective in mixing heat into the interior, not just relying on molecular motion. And when he came to think about what that could be, well, Walter Munk realized that you can actually check what motions exist in the ocean at depth. There are large current and what we call mesoscale eddies or large scale motions that are close to geostrophic balance. So where there is a balance between pressure forces and Coriolis acceleration. These numbers are associated with a Richardson number. The Richardson number is the ratio of the stratification, the change of density with depth, divided by the shear squared. It's a non-dimensional number. This motion has very large Richardson number. A very large Richardson number, motions essentially move along density surface. So if this is warm and this is cold, 2 layers of the ocean at some depth, well, motion move mostly along this density surface. They never mix properties across. So large scale motion cannot mix heat into the interior because they don't drive heat across interfaces. But smaller scale motion like internal waves can have a very much larger shear than geostrophic motion, so large that this Richardson number becomes order 1. And we know from work of Kelvin, Lord Kelvin and Helmholtz, that in that case, you can actually generate instabilities like the one I'm showing here that drive mixing across the two fluids and it can actually mix. So breaking waves due to Kelvin-Helmholtz like instabilities are effective at mixing heat into the ocean interior. This is, by the way, work that your colleague Dick Peltier has contributed significantly to. So we do understand that indeed there are spoons essentially are continuously active in the ocean interior in the forms of breaking waves, waves that live at the interface between density surface that occasionally break and mix, much like surface gravity waves. When they break, they mix some air into water. Here instead you're mixing 2 layers of different temperature or different buoyancy. So now the question that Munk posed to the community was, do we find these large mixing rates? And it took another, 40 years before people were able, maybe 30 years, before people were able to develop instruments that can measure this mixing very deep in the ocean, because we care about mixing at depths below 2,000 meters or so. And this is the surprise that came. This is work done mostly by the microstructure group in Woodsaw. The first time the experiment was done was in 1997 in the Brazil Basin. Here instead, I'm reporting results from a more recent experiment in the Antarctic circumpolar current down in the Southern Ocean, but the results are the same. What you see is that if we look at kappa T dBdz, this heat flux or the buoyancy flux, the product of these two that can be measured directly with probes like the one you see here, well, you see that the buoyancy flux is increasing with depth. So this kappa T dBdz is getting larger. So the mixing is more efficient at depth than it is at the surface. This is the mixing of heat, right? But now, if this is the ocean bottom, let's take the ddz derivative of this function. Well, what I'm saying is that the observation are telling me that ddz of that function is negative. It's decreasing with height. So ddz of this term is negative. The stratification in the ocean is always stable. What I mean by that is light water is always above denser water. So this term is positive, dBdz, and that implies that W is negative. So now there is a problem because it seems that Walter Munk was suggesting that mixing was diffusing heat into the interior and that allowed water to rise towards the surface. And now we're finding that what the observations suggest is that the profile of mixing is increasing towards the bottom, and the result is that the water is actually sinking instead of rising. So what is happening here? Well, we have to go back to the way Munk posed the problem. He said that he had an advection diffusion balance, but the diffusion is given by the Fickian law, which is ddz, the vertical derivative of kappa times the vertical gradient of buoyancy, dBdz, right? So if I take the derivative of a product, I have to take the derivative of the two terms in the product. So one term says a kappa t del squared bdz squared, and the other term is d kappa t dz times dBdz, if you want, right? If kappa is constant, this term is 0, and that is what Walter Munk was talking about. The stratification is positive in the ocean, and the ocean is more stratified at the top than at the bottom. The stratification is much larger towards the top, so the curvature is positive, so this term is positive. But the issue is that there is the second term, which is the change of diffusivity, of the rate of mixing with height. And here I'm showing for the same profile I've shown before, the profile of kappa t itself. And this is incorrect. This should have been kappa t, not log of kappa t. Sorry about that. So if you look at kappa t itself, well, the turbulent diffusivity is decreasing by 2 orders of magnitude as we move up in the water column. So it's this term that is strongly negative. And so apparently the fact that turbulent diffusivity, or the rate of mixing, is decreasing with height is driving sinking of water instead of rising of water. Now, this is not a result that applies only in a few places in the ocean. This more generically, if we start looking at what happens, this is a profile of mixing taken over regions that are pretty flat, so on flat plains. Yes, the kappa t doesn't change much with that. And there isn't much mixing, it's very weak. But every time you are above a ridge, like the Atlantic one, or the Pacific ones, or the Indian ones, or seamount, like the Sea Pacific rides, instead mixing rates are much larger, and they really increase towards the bottom. So there is always this tendency where there is strong mixing to be enhanced over topography and increasing towards the bottom topography. And we do understand why. It's because the way you trigger mixing is by having motions like barotropic tides or geostrophic motion that slosh back and forth over this uneven topography. And so you have these layers of density, one stack on top of each other, that have to move above non-regular topography. And so they be moved up and down. And so they trigger internal waves. They start oscillating and eventually they break. So it makes sense that mixing is enhanced along these regions. Indeed, analysis suggested that indeed mixing is all localized over this rough topography, new topography. These are more recent bottom topography forming the ocean, where we are forming ridges and new seamounts. And the velocity then are order of 10 to 100 meters per year here, because the upwelling is actually much more confined than you might have thought before, based on Munk's view. So now, how do we put the whole picture together? Because I just told you, and maybe now I can explain in even simpler term, that we have water sinking towards the ocean bottom because mixing is increasing with depth. And that's pretty clear. I mean, think about the water parcel sitting somewhere above topography, and it's being mixed more vigorously with denser water below than with light waters above. But what happens to this water parcel? Well, it's going to get denser because it's mixed more with denser water, and if it gets denser, it starts sinking. And that's why we get these funny results that because mixing is increasing towards the ocean bottom, water does sink instead of rise. This has actually been observed. The Brazil Basin experiment that I mentioned before is one of the first example where we measure profile of mixing all the way to the ocean bottom. Included also the second component to the experiment, a tracer, SF6 as sulfur hexafluoride, was injected in the ocean. That's a tracer that you can measure at very low concentration in the ocean. So it was injected just above the mid-Atlantic ridge here off the coast of Brazil. And it was released at the red dot in a very concentrated region, and then measured again 14 months later. And you tend to see that this tracer is definitely sinking down towards the topography. So we do actually see this happening for real. But now we can look at what happens once the water or tracer or water hits the ocean bottom. Well, now when the water is sitting on the bottom topography, it's still receiving heating. It's been mixed with the water above, because mixing and breaking waves are actually even more intense here than anywhere else. But now there is no heat flux, or if anything, there is some geothermal positive heat flux. So now this water parcel is actually getting warmer or lighter as a result of these heat fluxes. So water can get lighter and rise along topography in the deep ocean. So the idea is that water can sink towards the topography, but then can rise along sloping topography, like seamounts and ridges, where there is enough rough topography, there is strong mixing to drive this upwelling. I think in the interest of time, I'll skip these slides and just come to this point, at least what we can conclude is that this overturning circulation is indeed fed by this 15 Sverdrup water that is sinking at high latitude through convection. But then, when we are looking in the rest of the ocean, there is more water sinking in response to this mixing, which is bottom intensifying. So there is an additional 25 Sverdrup, and this we estimated using scaling laws for turbulent mixing in the deep ocean. So there is an excess 25 Sverdrup water that sinks towards mid-Atlantic ridges or Pacific ridges and Indian ridges and rises. And so there is an additional 25 Sverdrup for a total of 40 Sverdrups that sinks toward the ocean bottom. And all this water must be rising up along very thin boundary layers at the bottom of the ocean. So the reason why we don't see this in this picture here is that this picture, since it's averaging the interior ocean, it's a zonal average, averages what happens in the interior of the ocean and what happens in the boundary. Well, you're averaging 25 and 40 together because they are happening at the same depth in longitude, you're just happening a different place in longitude. And so when you average the two, you get just the impression that there is only 15 Sverdrup of water coming toward the surface and 15 Sverdrup of sinking. But what I contend here, there is a big compensation between water sinking towards region and seamount and water rising along thin boundary layer at the ocean bottom. And so given that unfortunately I have to leave at 4 o'clock sharp to make my plane and see all of you in person tomorrow, hopefully. Now I want to tell you that what we are really excited about is that we started an experiment in a new experiment to actually see whether we can see this fast upwelling of water along the ocean bottom. Because when we presented these new ideas about sinking of water along bottom topography, most oceanographers were very skeptical because the suggestion was, well, there was all this upwelling motion. Why didn't we see it? Why didn't we measure it already? You are predicting that it's very thin boundary layer, so they must have very strong velocity that probably we can measure. Our counter argument was that, yes, the problem is that generally you don't want to lower instrument to the ocean bottom right hitting the bottom, because it's generally a bad idea to hit rock at the ocean bottom with a delicate instrument. So we tend not to sample far enough at depth to see what might be happening at the bottom close to the sea floor. And so we started what we call the boundary layer turbulence experiment, or BLT experiment. Since there are a lot of recipes in this story, it seems appropriate to use a BLT for the name. The PIs, in particular the observational PI, are Matthew Alford, Marie-Jose Messias, Alberto Navera Garabato, Kurt Paulson, Eleanor Falca Williams. In particular, what I'm going to talk about today is work that was really led by Matthew Alford and student Bethany Winnie Katanak, and I'll show you what they've actually done to try to sample this deep upwelling of waters. We went to the Rockall Trough. This is a very deep trough. It's like a bowl, very rough. There is deep water that comes from the North Atlantic and sinks into this bowl, which is just off the coast of Ireland. And we went on this side where there is sloping topography, rough sloping topography. And we went and sampled what happens in this canyon right on the edge of this trough. And our idea was that now the canyon is nice because it's a confined volume, so we could just inject a tracer. This is what we did, or let's call it a dye. We injected a dye here within the canyon so that the dye couldn't really spread laterally too much, otherwise it becomes difficult to sample it. And our prediction was that we should see this dye in response to this mixing that increased towards the ocean bottom, something we verify, because there are strong tides generated here that break close to the ocean bottom. We would expect this tracer to start moving across density surface and move up, like by miracle, like if it was warmed up very rapidly across the seafloor. So we injected the dye just 10 meters above the bottom. Here, this experiment started a year ago, pretty much. In May of last year, where we injected the dye, and then, well, it's they, meaning the people more involved in the observations in this project. And they sampled this dye for 3 days with fluorometers that were being towed along, and some instead were fixed on moorings, and they were profiling up and down continuously. So we could follow what the tracer was doing over these 3 days. Since it's a fluorescent dye in this case, it just lasts 3 days before we lose the signal. But now I'm plotting the tracer, and I'm really plotting sigma bar, the mean average of density where there is tracer. So we were sampling the tracer. Wherever there is tracer, you measure its density, and you can essentially measure the bulk density of water tagged by the tracer. And so this is plotted in a temperature salinity space. So this temperature and salinity, and this constant line are lines of constant density. If we know temperature and salinity, we can compute the density of seawater at a particular depth, the depth of the tracer, just by the equation of state. So now when we put the tracer in, it had some temperature around 3.75 degrees Kelvin, degrees Celsius, sorry, and 3.34.93 or something salinity units. with a density which is slightly higher than 27.75 since it's below this curve. And now we see that after 3 hours, after 15 hours, after 19 hours, this tracer is moving along this line, meaning the density of the tracer is decreasing. We see that in a matter of 3 days, the tracer got much lighter, all the way to 27 point, I don't know, what is this, 7.2, it must be 7.25. This change in density is dramatic, especially such short time scale. Indeed, we can estimate what was the upwelling rate associated with the change in density, because we can look how long it took and how up in water column the tracer ended up. And it was an upwelling rate of 100 meters per day. You remember that this is not meters per year, but meters per day. Indeed, we expect this water that rises along the bottom, since it's confined to a very thin layer, to have very large velocity in order to balance all this water that is sinking in the interior. So this is the first observational evidence of this strong upwelling along the ocean bottom. We do actually observe water getting very light as it slides over bottom topography. And I'll stop here, just concluding saying that bottom intensified mixing drives a pattern of up and down welling along ridges and seamount. So bottom intensified mixing drives sinking towards the topography, but then the water rises along ridges and seamount. The Brazil Basin documented the downwelling in the 90s. And our BLT experiment instead is the first evidence of this very fast rising motion along rough topography. The net exchange of water between boundary layers in the interior sets, this is something that we'll get a bit deeper into tomorrow. This pattern of upwelling and downwelling has important implication for setting the overall ocean stratification and overturning situation of the ocean. And it also affects or makes water age distribution very non-homogeneous, because water that are getting older as they sink, but instead they rise very rapidly. And just to conclude, essentially, the picture you see here, you have sinking of water at high latitudes in this abyssal cell. And what you're not seeing in this picture, there is a lot of water that upwells very rapidly along ridges and seamount, compensated by water that sinks in the interior at a slower rate, but over a larger area. And I should acknowledge, well, NSF for supporting the research, but importantly, all the great colleagues that have worked on this question, Jörg Canlis and Henri Drake as former student, Ali Mashayek was a former postdoc and actually a former student of Dick Peltier, Sophia Merrifield, student, Max Nikorashin, another student, Kelly Ogden, a postdoc, and Trevor McDougall, a great and inspiring colleague from Australia. Thank you very much, and I can take a few questions.